biologists. Today we're going to talk about population ecology, so get yourself a pen and get ready to take some notes. Alright, so the first thing we want to do is define population ecology. Population ecology. And what that is the study of populations and how they interact with their environment. I'm going to abbreviate population this entire time to just make it easier on us. So how populations interact with the environment. And remember, a population is one species in one place at one time. So there's a population of humans in my house, but a separate population would be domesticated cats in my house, and a separate population would be the types of plants, each species of plant that I have in my house. So population is one species in one place at one time. And when we think about population ecology, there's really three main characteristics that we use to talk about population ecology. Three main characteristics. The first one is population density. Population density, which really means what's the range of your population and what's the size. Is it really crowded in a small space? Is it really sparse in a large space? That's population density. Okay, we're looking at my computer now because I want to show you an example of population range. So here we have the country of Australia, and outlined in this little black dotted line is the range of where you find kangaroos. We have different densities of kangaroos, so the dark red is more than 20 kangaroos, and the light yellow is 1 through 5 kangaroos, and the blue is less than 0.1, so rarely a kangaroo. Now we like these ranges because if I were going to study kangaroos, this range helps me determine where I should go. I'm not going to have very good luck studying kangaroos in the Northern Territory. I'm going to have a lot more luck if I go down here to New South Wales, where the density is higher. We also use ranges to figure out how a population's area is changing over time. That's this. Here we have the outlines of states, so that was California, here's Nevada, here's Oregon, we got Washington, Idaho, Montana. So this is the range of the sage grouse, which you watched a video on. It has really awesome mating calls. And the red is the historic range. So it used to have a wider range, and then they recounted it in the year 2000, and they found that the current range is restricted. So where you used to have a lot more grouse up in Washington and parts of Oregon, now it's restricted to the southeast corner of Oregon. So we use ranges to see where we can find species and how the species distribution is changing over time. All right, back to our notes. Now that we've seen some examples of range, the second thing that we look at when we talk about population ecology is, get a better pen, dispersion. So dispersion patterns are going to be clumped, random, or uniform. You read about that in your book. Clumped are usually things that like to live around resources, or there's safety in numbers. An example would be a school of fish. They're all clumped together, so their dispersion pattern is clumped. Uniform is when, like, birds create their nests pecking distance away from each other, so they're uniformly spaced out so they can't peck each other. Another way of looking at this would be like if you looked at a subdivision from above, all the houses are uniformly spaced out, except humans tend to live clumped. We live in cities mostly. And then random, this is the most rare in nature. Random is usually wind dispersed things, like dandelions or seeds that fly far away. Wherever they land is where they live, and it really isn't determined based on where the other individuals are. So here you kind of live together, and here you're intentionally spacing out, and this is like whatever. So that's the dispersion pattern. And then the last thing we talk about when we talk about population ecology is how your population changes over time. And this one is the biggest one. This one gets really complex. We want to think about demographics. And what that really means is your age structure. So you're going to watch that video about population pyramids. Your sex ratio. Is there one male for every female, or are there 5 males for every female? Your generation time. Which is the time from birth till the average birth of another offspring. So if humans usually have kids by 22, our generation time would be 22 years. If humans usually had kids around 15, our generation time would be 15 years. So your birth to the time of your first offspring, that's the generation time. Then we want to think about how many offspring do you have at once. Fecundity, we've talked about that. And how many offspring can you have over a lifetime? Humans, you can get pregnant pretty much once a year, so we can have like 1 to 2 babies per pregnancy is regular. You could also have up to like 6 or 8, but that's usually induced with fertility drugs. And then if you just have them back to back, that could be a high fecundity. Then we're also going to think about the birth and death ratio. So, are you adding more people than you're losing? Are you losing more people than you're adding? We're also going to think about immigration and emigration. Are more people joining your population or more people leaving your population? So leaving, joining. You're immigrating into somewhere, you're emigrating away from somewhere. Now, all of these ideas can get really complex, so we like to organize them using equations. Let's identify a couple different variables before we look at the equations. First, if you see a little triangle, that's called delta, and that equals change. N is your population size. Sometimes it's lowercase, sometimes it's uppercase. B, which is always lowercase, is the birth rate. D is the death rate. And then R is going to be the growth rate. All right, so let's look at an equation. If we want to figure out how our population is changing over time, we could look at the change in the population size, which will be equivalent to your births minus your deaths plus your immigration minus immigration. So births minus deaths, how many people are joining or leaving, that could be positive or negative. Same here, will equal how your population size is changing over time. We could also figure out our population growth rate. To do that, we would be R, which is equivalent to the births minus the deaths. Are you positively growing? Are you increasing in people? Or are you negatively growing, which is decreasing in people? And then to combine these two ideas, you have population growth, which is equivalent to your growth rate times your population size. Now this is interesting because if your population growth if it's unchecked, you could have exponential growth. And when we talk about exponential growth, we always say it's shown with a J-shaped curve. That's a U, curve. And what that means is if you were to graph your population over time, so this is going to be time, and this is going to be my population. So here's my population, smaller, getting larger, here's time, less time, more time. You would end up having, your population growing slowly at first, and then just shooting upward. That's that J shape. So that's your exponential growth curve. Get another piece of paper ready. All right. So we have an equation for exponential growth, which is awesome. And the equation is the change in population size over the change in time, T is going to be time, equals your births minus your deaths times your population size. What's cool about exponential growth is, that's supposed to be an arrow, it usually only happens until you hit some kind of controlling factors. So it's temporary unless controlling factors are removed. So controlling factors would be something that stops your population from growing. You run out of food, you run out of space, something that just won't allow your population to grow anymore. We have a term for all of our controlling factors kind of together, and it's called carrying capacity. What is the capacity your ecosystem has to carry life? We represent this with K, because we're going to have equations for it. And K equals the maximum number of individuals and environment can sustain. So how much can it carry? All right. If you're not exponentially growing, If you reach some kind of carrying capacity, then we call it logistic growth. So logistic growth does not have that J-shaped curve. So up here, J-shape. Logistic growth instead has a S-shape. And I think this is kind of easier to show than explain with words. So if I graph my population changing over time, so down here I have time, and up here I have my population size, so it's increasing. Now I get to consider carrying capacity. So let's add K to this graph. We'll say K is right here. So that's the largest number of population right here that can be sustained by my environment. My population is going to start off slow, and it's going to grow, and it's going to grow. And now this looks like a J-shaped curve, right? And maybe it is if we looked at it just now, like if we didn't see the rest of it, but if we continue to watch it, as your population approaches K, the growth rate's going to slow. It's going to kind of slow down and settle out, and it's going to approximately hang out around your carrying capacity. So it's going to level off where the carrying capacity is, because theoretically it can't exceed the carrying capacity. The carrying capacity is the max number of individuals that your environment can support. So if my exponential growth were to go past it, if it were to increase, then something would happen. We'll talk about that next. Now, logistic growth can also be represented with an equation. The equation for logistic growth is delta N, so the change in population size over delta T, the change in time, is equivalent to your growth rate, but the maximum. So your maximum growth rate times your population size, and then your carrying capacity minus N over your carrying capacity. So let's break this down. We know what these things mean, these three things. We've already talked about those. But K minus N is also its own equation. That's the number of additional individuals a population can support. That would be how many more can we fit in? And then if we take K minus N over the carrying capacity K, that is equivalent to the fraction of the carrying capacity that is still unutilized. The fraction of K that is not being used, because this is the number of individuals that K can still support, divided by your carrying capacity. So let's check this out again. Your change in your population over time is equivalent to the growth rate being just about the same as how much you have left in your carrying capacity to grow to. Now, if you don't have any room left, if you've hit your carrying capacity, then this would be 0, and you would have no more growth rate. So your logistic growth kind of peters out, and that's why we end up with this leveling out. Unlike exponential growth, where K was not even a factor. In exponential growth, you're just skyrocketing upward, your population keeps growing, and then if you pass your carrying capacity, a whole bunch of things might happen. Let's talk about those things. All right, we are looking at my computer again, and I want to show you two cases of exponential growth that happen in the real world in nature. One is algae. Algae have a seasonal cycle, and what happens is, they grow kind of in a low population density until conditions are right, it's the summer, they're going to just start to exponentially grow, and then when they reach their highest point, they die back and then start doing it again. So this is every year, there's a seasonal peak. We call this a boom and bust cycle. The population booms and then it goes bust, but it doesn't die out. So your population don't go extinct, they just go back to the lower level, which is more of its equilibrium level. Same thing happens with lemmings, which are like these little rodents you can see in the background. They have a 4-year boom and bust cycle. So every 4 years, roughly, 1, 2, 3, 4, their population spikes. Here it was 3, spike. Here it's 4, population spike. And that pattern just continues. After a big boom year, the population tends to be lower, notably. So there's your bust. Boom and bust. We also see this pattern happen with predator and prey. So here we have the abundance of lynx, which are predatory cats, 20, 40, 60 to 120. And then over here we have the abundance of hares, which are rabbits. So a larger scale, going up to 200. Then we have the year, since we've been tracking it. And let's look at the hares first, which is the blue line. So as this population grows, its predator has more food and can also grow. More predators mean less prey, so the population crashes, which means less food for the lynx, so the population crashes. So more prey, more predator, less food, less predator. And you get these boom and bust cycles for both species. Fascinating, right? Now in the notes we were drawing what might happen if your population continues to grow and surpasses K, our carrying capacity. And there are 4 options. So first let's orient ourselves. This is the consequences of exceeding the carrying capacity, which is the maximum number of individuals an ecosystem can support. Here we have time. And then this is your population size here. So you start out with nothing and you go to more. We don't have numbers because this would be different depending on what your species is, but this is an increase in population. So let's first look at the red one. Here I have my J-shaped curve, so I'm getting exponential growth. Here's my carrying capacity. Now, if I exceed my carrying capacity, we say it's overshoots. If I overshoot my carrying capacity, I'm most likely going to end up damaging my environment or running out of resources. So after I exceed my carrying capacity, I'm going to start to bust, which is what we saw with the algae and the lemmings and the hare and the lynx. So as we bust, one option is that our population goes extinct and dies out. So that's the worst case scenario. Another option is that our population exceeds K, starts to bust, and then kind of just like bounces back, but at a much lower level. So because of the damage done of exceeding our original K, we then have a reduced K, and now your population has to sustain at a lower amount than it would have if it did not have exponential growth. The last option is you could exceed K, but it looks like almost starting to become logistic growth. If this green line had bent and stayed under K, then we would have called it logistic growth. But it exceeded the carrying capacity, and now it's kind of just hovering around the original carrying capacity. So this allows a lot more of your population to exist, and it's kind of like petering. Sometimes it's a little higher, sometimes it's a little lower. Yeah, that would be great. And we're talking about this now because humans, unfortunately, or fortunately, I don't know how you feel, this is the human population. Starting back at 1200 BC, and then this is now. We were really slow growing, really, really slow. And then we started to get a little better at reproducing. There was more of us, but still pretty low. The bubonic plague took us a lot out. Like, that was a big population drop. And then, for the last 1,000 years, look at that population growth. Like, that J curve is so, so sharp. We're just exponentially growing. Right now, we're at 7-point-something billion humans on Earth. We don't know what's going to happen with our population growth. We used to speculate that the carrying capacity of Earth was around 5 billion, and now we're up to 7. Some people speculate that it can get up to 12. We don't really know, but we do know that when we see other populations, one of these 3 things is most likely to happen. We cannot continue to exponentially grow in a finite amount of space with finite resources. So you might be curious, how many people are there on Earth right now? So here is the United States Census Population World Clock. Here's the US population. Ooh, do you see it moving? We have 1 birth every 9 seconds, 1 death every 11 seconds, 1 international migration, net. So some people leave, some people gain every 666 seconds, and then a net total gain of 1 person every 40 seconds. So now we're already up to almost a second person here. Notice how slowly this is moving compared to the world population. So we're at 7.75 billion right now. And this is being recorded on March 24th. So when you check it out for lecture later in the week that you're currently in, this is going to be higher, much higher. All right, let's put this idea to practice. Look at the data below and decide what can be said about survival and clutch size. Clutch size is the average number of eggs laid in it could be a nest or a corner or rocks, wherever they lay their eggs, but that's what a clutch is. And then here you have the probability of survival to the following year. So what is the general trend? The trend seems to be your survival decreases with the number of eggs in a clutch. So the more eggs in one nest, the less likely you are to survive. All right, thank you so much for our lecture. We covered the 3 main characteristics of population ecology, the equations that we use, and the difference between logistic growth and exponential growth, and what happens when we exceed the carrying capacity of an environment. So email me with questions, and I look forward to hearing from you. Have a good week.